All right, hello everybody. Welcome to our project two. Us three, we have
Or I have
Jose.
to share screen first.
Okay, no, you're good. No, you're good. You're good. Go ahead, Jose. You want to share your screen, and then what we're gonna do is we're gonna kick off with Jose. That we're gonna do the project, the part one first, and I'm gonna introduce all the functions that we use, and then we're gonna head it to Edison Juncheng for his part two. All right, go ahead, take it over, Jose.
Okay, so hey everyone. So I did when I did part one here. So just to start off, let's just answer the first question, which was so what is the advantage of the D index within the D index and the other classifications we did. So D index was introduced by Dr. Han, and it was a proposed evaluation metric that was designed for classification problems when there was like imbalance scenarios. It specifically is good because it offers like advantages over more traditional methods, and it's you're able to adjust it its everything and the way it performs based off like sensitivity, and then it just gives you like a better understanding of certain behaviors. Also, I guess the D index can help kind of identify singularities and optimize the kernel selection. So we kind of went through different like kernels too, and even scaled the data with different methods. But we'll go into that a little bit more later. So the next question was just how we calculated the index for the multi-class classifications. So essentially for that, we kind of you just treat like every class as its own like binary classification problem. And then you just kind of consider the positive classes with the remaining as being negative, and then you calculate each D index for each classification, and you just kind of keep track of those. And then you can also like get like the weighted average methods and kind of calculate the averages off that, and kind of like you can even tune that if you needed to, but we didn't really do that in within this specific problem. So for the way we calculated the index was based off of this formula which we got in class. So essentially you can also even use this specific function just to get other things like the sensitivity, specificity, and accuracy. Just we had to create a modified version of this just to handle like the multi-class, which we'll show on the next slide. And essentially, here's the one I was talking about. This was specifically just to handle the multi-class calculation. So it kind of goes over the things I mentioned earlier. We relied on the other formula, and then we kind of do a one versus all manner where it returns kind of like the average across all the classes. And then it kind of just computes the measure function, or uses the previous function to do that. And then just gives us kind of like an overall like evaluation. And then just for the remaining metrics within part one, we use, obviously you see the D index here is what we use for the F1 score for the micro and macro version, for the balance accuracy, and the ROC score with is the functions we used. And then, so you'll see in a sec, but essentially our problem kind of yielded like near perfect results with just the iris data set. So we kind of had to like add a noise or add like make the problem more complex just so we can actually compare the differences. And all we did that was just kind of created like random features and just kind of added that into like the data just to make it a little bit like harder, if you will. And then just to further prepare our data, just for the ROC calculations, we just kind of just use like these like evaluation metric with by binarizing the labels just to so we can like specifically use it for that section. And then we ended up doing kind of two types of plots just to show our results. One was like the one versus the rest OVR, which is kind of used just to compute each class against all the other classes. And it was essentially the way we did that. We just kind of iterated over all the classes and kind of computed the RC curve, and then kind of got the area from that too. And then the other plots we're going to show is the 1 versus 1 multi-class. And essentially this one is just kind of computes a pair of the classes like separately by themselves. And then it kind of treats it as a classification problem from there. And then you can see the code here. And then this can be kind of where we kind of group everything together, and it kind of shows like our kind of like all our results, but just on one graph. And it's kind of really what this is going to do. And then this is just going a little bit more in depth to that, and just kind of shows how we calculated the macro average for the 1 versus 1 curve. And then this was kind of what I mentioned earlier, how before we added like the noise to our data, everything just kind of performed perfectly. So we kind of really couldn't get anything from that. And that's for the second plot. Just to, I'm sure y'all can see, but just to show y'all the reason we have 3 here is just because there's 3 different types of classifications within the data set. And this was the second plot I mentioned. And then, so once we kind of added the noise, it did kind of simplify things a little bit in terms of kind of being able to see what the performance was. We used the linear kernel for here, and you can see kind of the d-index scores here, the F1 scores, the accuracy, and the AUC score, and then you can kind of visualize them over here too. And then for the other plots, these were the reserves for the other classifications within that. And then just so we kind of got a little bit better of a picture, we kind of did the same thing just on the remaining kernels. And just to like simplify, we didn't add like the whole pictures to everything, so we just kind of wrote down the results here. Just give y'all a quick sec to look if y'all need to. But just to summarize kind of what happened with this little portion, the linear and the custom kernels were the ones that kind of consistently performed the best, and the polynomial was consistently like essentially the worst. Later when we kind of scale the data, you'll see that it kind of improves a little bit. And then just to go over like the broad things, what we did with the scale data, this was kind of the results within the mix max scaling method. You'll see the results are still pretty good here, which we'd expect with the linear, still consistently one of the best. And one of the trends you'll notice here is the sigmoid will actually start performing pretty similar, if not better than the linear kernel in some instances, once we start scaling data a bit. But you can see even things like the polynomial and the RBF start performing a lot better than what they did on other ones. And that's just a visualization of that one. And then this was just for the standard scalar. Those were the results for that, and that's kind of the visualization for it. And then just for the robust scalar, we did the same thing. This actually was the one where as a whole, everything kind of just performed the worst, but here's a visualization for that. And then the max absolute scalar, here were the results for that. And this was the visualization. And then just kind of summarize, as I mentioned a little earlier, but essentially within this one, everything kind of performed the best with the mixed max scalar, specifically with the linear and the sigmoid kernels. And even though, and the other ones ended up kind of performing a little bit better, but specifically like the polynomial, but it still kind of like had a lot of issues, but it's kind of still a little promising thing to look at. And then I guess this is where we'll go to part 2.
All right, y'all, that was a good job, Jose. Well done. That was awesome. Let me share my screen now, so I can go over that our parts right here. All right, cool. So there we go. All right, cool. So what we did here, what basically is since we have 3 different data sets. So what we want to do is we want to declare a function instead, just, doing all the method over and over again. So what we have here, basically, we're using the sport vector machine and also the one with the bagging method right here. So see this slide right here, we used pretty much 3 functions. We declared the first one, the compute measure, which we measure all the scores. The second one, simply the original sport vector machine. And then the last but not least, we're using the bagging method, which, you imply different 3 different training data, so we can come out result as a whole. So first off, we have the compute measure, what's our name is called. Of course, we have true label and predict label, calculate all different accuracies that, Jose already mentioned earlier. We have, accuracy, the first one, sensitivity, specificity, and precision. And on the right, here's a screenshot of some of our functions here. Since we have to calculate all the trues, false, positive, and all the scores right here. Here is a screenshot that you can see. Jump onto the next page. Yeah, we got more scores over here. We have the NPR, and also we got the F1 score, and also the index score, the D1 score over here on the right. That's some more equations that we have on the right. And yeah, that's pretty much the first function that we declared. Once we declare this function, we just, every single data set, we just return a result, which is really convenient. And the second one that we have, the sport vector machine procedure that we have. Same thing, split the data into training and testing first step, and then, train the model, predict the test data set, and, store all the labels. Of course, we extract all the true label that we want to match them up with, the true labels. We don't want to cause any confusions. And then jump to the next, we, of course, calculate all the measures and for the predict labels and the true labels. Last but not least, we calling a matrix display, which displays all the graphics that is gonna shows all how the accuracy goes and how the sport vector machine module predicts. We're gonna show the graphic in a little bit. Edison Juncheng is gonna take over in a little bit and show you guys how the result looks like. And then we have a screenshot here. This is our function that declares the perform sport vector machine. Small, pretty short function, but it helps a lot. It saves a lot of space and saves a lot of time. Last but not least, we have the bagging method, which is very important. Pretty much all the procedure it goes. We picked 1/2 of the data from training, and then from the of course 3 different training data sets, and we named them training 1, 2, and 3. We run the algorithm, and then we predict the test data, same thing. And not last but not least, of course, we're gonna do the majority voting. This is one of the important thing about bagging method. We get all the result, and then we use majority voting and gets the result. And of course, we evaluate the performance. Going to the next, we have all the function declared here. Look at this. We have sport vector machine 1, 2, 3, and then of course training, testing, the second half, and here comes the result. And we're gonna print out all the graphics. All right, and I'm gonna hand it over to Edison. Juncheng, you're gonna
Yeah, sure.
Stop sharing. All right, cool.
Can you guys see it?
Yeah.
All right, here's just we're loading the 3 data sets. We have 3. The first one is credit risk small data. The second one is credit data simulate. Third one is cybersecurity. Credit data pre-processing. This part we extract the true labels and we check data balance, and we normalize using standard scalar. The data is not balanced at all. The entries labeled as 1 has 1540 entries. However, zeros only have 130. And here we're performing the SVM on the credit data, and we have a perfect results. Here's the results of bagging SVM on credit data, and also a perfect results. And for the credit risk data pre-processing, we pretty much did the same. Since we are comparing the performance of 2 different models, we want to use the same standard scalar and the same kernels. And also the data set is imbalanced. And here's the results on the credit risk data, and everything is it's so perfect. And here's the results for performing bagging SVM on credit risk data, and everything is still 100%. And for pre-processing cybersecurity data, we extract the true labels, and we count all the labels, and we convert label -1 to 0, and we normalize with standard scalar. And this data set is also imbalanced. And here's the results of SVM on cybersecurity data. And we have a 98% accuracy, but a sensitivity of 0.5, which means that two labels that were 1 were predicted as 0. We have the same results for the bagging SVM. Yeah. And here's the conclusion on SVM versus bagging SVM. For all 3 data sets, the classification is imbalanced. And to compare the performance of SVM and bagging SVM for the 3 data sets, I applied the same standard scalar, and used the same kernel for SVM, since it works well for credit data. And as a result, for all 3 data sets, SVM, bagging SVM generated the same output. And for credit risk and credit simulate, both generated the best possible output. To conclude, due to the imbalanced data set, our result is not able to compare between the performance of SVM and the bagging SVM. And for further analysis, we will try to find some different data sets that were more balanced. Thank you.
All right, that was awesome. Thank you, Junchang. That was a great job. Anything, Jose? Anything that you have concluding? Anything you gotta say?
I mean, no, for the most part, no. I think you can see with the SVM, it's able to kind of kind of do really good wonders with this type of data.
Right.
And so it was really more like trying to figure out how to kind of make it more complex, and it could just be that it did such a good job anyways, but even once we kind of made it more complex, you would see that it would still get a lot of things right. So I think it's really good to find the different types of classifications and just kind of evaluating it off performance kind of based off that. But yeah,
definitely. I noticed the balance of the data is very important. So maybe in the future, whenever you have a data set, you're gonna look at it, make sure it's balanced, and what we gotta do is we gotta choose the best machine learning algorithm to implement the problem. All right, Juncha, anything? If
Yep.
you have any
Yep.
question, that's great job. And thanks everybody. And yeah, we'll see you guys around.
Thanks.
All right, thanks.